So the last time we talked about finding the work required to do some type of task. And today we're going to talk about the distance that you go if you're traveling at a certain velocity for a certain amount of time. Although those two things might seem non-related, I want to show you some similarity. Work was equal to the force times the distance that you moved that force across. To find the distance, we're going to take the velocity times the time. So in both of them, you're multiplying one thing times the other. So if the force was 200 pounds, and you were doing it over a distance of 6 feet, you'd multiply it together and get 1,200 foot-pounds. If the velocity was 200 miles per hour, and you did it for 6 hours, you'd go 1,200 miles. So miles per hour times hours, or your force times your foot-pounds. Now, the thing that made things difficult, because it seems like a really easy calculation, what do we need calculus for? You don't if the force happened to be constant. And the same thing would be true if the velocity was constant during your whole trip. But often that isn't the case, just like the force isn't always constant. So what did we do yesterday? We took the force and put it here. Now we're going to take the velocity. And here we put the position of the force. Now we're going to put the time. So we're just changing our dependent and independent variables, and we're going to go from not position A to B, but from time A to B. So instead of dividing this up into n positions, we're going to do it into n time intervals. So we're going to call this, instead of x sub 0, t sub 0, and this is t sub n, and then we're going to take the kth interval from tk minus 1 to tk. So we're assuming we have some type of velocity as a function of time that's not constant. And we're going to take this kth interval, and what's the time from tk minus 1 to tk? We're going to call that delta t sub k instead of delta x sub k when the variable was x. And then we're going to pick some time between these two times and call it time c sub k, and put that into the velocity equation and get v of c sub k. So what happens now, I'm going to take the area of this rectangle. What is it going to find? It's the velocity times the time. The area of that rectangle finds the distance that you went in this time period. But we have n time periods, so we have to add them up from k equals 1 to n. And what are they? They're the velocity, v of c sub k, times the time, delta t sub k. But we still have that little bit of error because the velocities are constantly changing. We can't really hold it the same during this whole time period. So what we do to avoid that is to take the limit as n approaches infinity. And then these time intervals become so small that we're really adding up straight lines instead of rectangles, and we don't get that error. Nicely, this is exactly what we originally defined a definite integral to be, an infinite Riemann sum. The only difference, this was f of c sub k instead of v of c sub k, and this was delta x sub k. So the only difference is the function is different and the independent variable is different. So this doesn't give us the integral of f of x dx, it gives us the integral of v of t dt. So that definite integral from t equals a to t equals b will give us what we wanted to find. Now, there is one thing that we have to be careful of. Distance is always positive. And in this case, I have my velocity as always being positive. But there's no saying that the velocity can't drop below the t-axis. In which case, the velocity is negative. If you add up v of c sub k times delta t sub k, you're going to get a negative contribution. And you don't want that. You want it to be positive. So what we do to avoid that is if the velocity is negative, just make it positive. So we make an absolute value on there. Now this finds what we're trying to find. The distance traveled from time t equals a to t equals b. Now, before we go on, I wonder if this other thing had any meaning. Would you ever just want it without the absolute value? Well, consider this. Velocity, when it's positive, it means you're gaining position to where you're trying to go with respect to time. So if I'm trying to go in this direction right here, if I have a positive velocity, like 200 miles per hour, and I go for 3 hours, I'm going to go for 600 miles in a positive direction. But if then I go a negative 200 so that I'm losing position for 3 hours, I end up back where I started from. So I ended up in the same place. What I would say is my displacement, my change in position was 0. And sometimes you really want to find your change in position. You don't really want to find the total distance, but you really want to find out what your change in position was, where you ended up. So we call this the displacement. The change in position is called the displacement. And that could end up 0, it could end up positive, it could end up negative. Distance will always be positive. So in that example I just gave, if I went 600 this way and 600 that way, my distance would be 1,200 miles, my displacement would be 0. And both of those are a value. So I'm going to say that both of those two equations we want to know. So let's try an example. We have a particle moving along the y-axis here. And it starts out right here at 0, 2. And we want to know two things. Where does it end up? And how far did it travel? Well, how far it traveled is going to be the distance. So I know I need to find that. And to find out where it ended up, I'm going to have to find the displacement in order to answer that. So I need to find both of these things. And what was I given? Luckily, I was given the velocity, where the velocity is in feet per second and time is in seconds. So the easiest of these two calculations is usually the displacement, because there's no absolute value. Absolute value always makes things a little bit harder. So I'm going to find the displacement first. It's the integral from -1 to 4 of v of t dt. And I can take that antiderivative, and I get t cubed minus 3t squared. And I get 64 minus 48. And when I put in -1, I get -1 minus 3. So 16 plus 4 is 20. Now, it never really asks for the displacement. It asks for where it ends up. Well, if it started out at 0, 2 and displaces a positive 20, it's going to go up here. It's going up and down the y-axis, so it went from 0, 2 up to 0, 22. So that would be one of your answers right there. Where did it end up? Now, to actually get the distance, now you've got a more difficult calculation. You have to take the absolute value. And we don't have any antiderivative functions for absolute value. So what I'm going to have to do is hope that the velocity is always positive, because then it's going to be the same answer. But I don't think that's the case here. If I factor that out, if I take out a 3t times t minus 2, and if I put the velocity from -1 to 4 on the number line, I find out at t equals 0 and at t equals 2, that's when it's stopped. And anywhere less than 0 gives a negative times a negative or a positive velocity. Between 0 and 2, I get a positive times a negative or a negative velocity. And greater than 2, everything is positive. So what I have to do is take the integral from -1 to 0 of 3t squared minus 6t, and realizing that the velocity is positive, that's going to be the actual distance. But when I take the integral from 0 to 2 of the same v of t dt, now I have to put a minus sign in front of that, because I know my velocities are negative during that time period, so it would give me a negative contribution to distance, and I don't. I want it to be positive. And lastly, I go back and I go for positive in that last integral. So I've got 3 separate integrals to take. Now you could actually do them without a calculator. If you had a calculator, it would be easier. In fact, if you have a graphing calculator, it's actually quite a bit easier, because there is an absolute value button on your calculator, so you could do it with just one integral. But we really don't want to have to always use calculators, so it would be nice to do it this other way. But instead of doing it this, you already know how to plug in all those, take antiderivatives and plug in those numbers. What I'd rather do you instead is show you a different way to do this problem. And this is going to lead to your overall understanding how calculus works. What if instead of considering this as a distance displacement problem, what if we considered this as a differential equation? V of t, what's another way of saying v of t? It's ds dt. Velocity is the rate of change of position with respect to time. If we said that equals 3t squared minus 6t, we've got a differential equation that we can solve for s. Especially since we have an initial condition at 0, 2. So I know that at time, well, this is the position 2, and that's at time -1. So I know when time is -1, I have a position of 2. So I have a differential equation with an initial condition. I can actually find the position equation for this particle. So I take not the definite integral, I take the indefinite integral, and get t cubed minus 3t squared plus c. And now I plug in, my position is 2, -1 minus 3 plus c. C turns out to be 6. And now I've got an equation. T cubed minus 3t squared plus 6. And then I can just find out the position at the important times of this trip. At the beginning, at the end, and at the 2 times it stopped. So if I put in -1, I get -1 minus 3 plus 6. So I get 2. If I plug in 0, I get 6. If I plug in 2, I get 8 minus 12 plus 6. I get 2. And if I plug in 4, I get 64 minus 48 plus 6. I get 22. So now can I find out the distance? I went from 2 to 6. So that was a distance of 4. Then I went from 6 to 2. I went in the negative direction, but that distance is still 4. And then I went from 2 to 22. So I didn't really go just from here to here. I went from here to 6, back down to here. I said I went. Actually, the particle did that. So it went a total of 28 feet in that 5-second period. Now, if you'd actually done these integrals, you would have gotten the same thing. This would have been 4. This would have been 4. And then the last one would have been 20 if you did this 3 integrals. So 2 different ways of solving the problem. And do you see the displacement this way? It went from where? It went from 2 to 22. We see the displacement was 20. So let's go to 2 more problems, and then if you can understand all 3 of these, you really will understand distance and displacement. So instead of a particle this time, it's more interesting. We've got Roger Rabbit. And he's not on the y-axis, but he is leaving the origin. So he's right here at the origin, but he's headed east. So at time 0, he's right at the origin, but he's heading east with this velocity equation. Now, as it turns out, that means that when this velocity is positive, he's heading east. When it's negative, he's heading west. And at the very beginning, when t is 0, you can see this is negative. So even though he's trying to head east, at the beginning, he actually goes west. The question is, how far does he travel? That's the distance. And where does he end up? Which is going to require the displacement. So, what do I do? Well, let's just find the displacement first. The displacement would be the integral from time 0 to time 5 pi over 6, and v of t is negative 4 sine of 3t dt. And you could take the negative 4 right out front if you wanted to. So, what's the antiderivative of the sine of 3t? Well, it's minus, so minus the cosine of 3t, but then divided by 3. So we get 4/3 times the cosine, 3 times that, so 15 pi over 6, or 5 pi over 2. So the cosine of 5 pi over 2 is same as the cosine of pi over 2, or 0, and then the cosine of 0 is 1. So the displacement is negative 4/3. So if it started out right here at the origin and displaces a negative 4/3, where is it going to end up? It's going to end up at negative 4/3, 0. And we've answered the second part of the question. Now to get the distance, again, I'm going to have to break this up because I'm going to have to find the absolute value. To get the distance, I have to take the integral from 0 to 5 pi over 6 of the absolute value of minus 4 sine of 3t dt. Oops. And I can see that as being a problem, quite a bit of work. So I'm going to try to use my knowledge of graphs. What do I know about the sine function? At time 0, it's going to start out at 0. But because this is the sine of 3t, normally this would be pi over 2, but it's getting compressed by a factor of 3. So all of these distances, instead of being pi over 2 apart, are going to be pi over 6 apart. So when you graph the sine function, you're going to go, the sine of 0 is 0. At this first point, usually you're up at 1. But here we're going to be at negative 4. And then we get back to 0. And then we go up to 4. And then back down to 0. And then back down to negative 4. Now, why this is so valuable is because if you divide this up, all of these little sections in here are the same. So if it were me doing this problem, I wouldn't have even done this first one. I would have just found the area in this first little section. I would have taken the integral from 0 to pi over 6 of minus 4 sine of 3t dt. And then you would have ended up with 4/3 times the cosine of 3t from 0 to pi over 6. Well, the cosine of pi over 2 is 0, the cosine of 0 is 1. You'd end up with negative 4/3. So I would know right now that the area of this little segment is 4/3. Once I know the area of that is 4/3, can I find the distance? Yeah, the distance is just going to be 1, 2, 3, 4, 5 of these 4/3, or 20/3, and it's in meters. And how would you get the displacement? Well, you can see that this would cancel with this. This is the same amount of negative area as this is positive. So all I'd have to do is see the displacement is this negative 4/3, and then I could find out that it ended up at negative 4/3, 0. So I'm just hoping you can see, if you have a little bit of knowledge of functions, the only integral you'd have to take is this, and you'd be able to answer both questions. Okay, so let's go to one more where we have Amy the ant, and she was crawling along in the xy coordinate system. She's crawling along y equals 3 from t equals 0 to t equals 6, and she starts at the point 2, 3. And for the first 3 seconds, she's got this velocity, and for the next 3 seconds, she's got this velocity. So she has a piecewise function for her velocity. So the question is, how far does she travel and where does she end up? Well, I think if you wanted to do the displacement, which is the easier one, you have to take the integral from 0 to 6. But we would have to go from 0 to 3 with this velocity, and then from 3 to 6 with this other velocity. And that would give you the answer. Well, we've got a slight problem. This is pretty easy to do. This one, you don't learn how to do until you get to Calculus 2. And it's pretty tough. So if you did not have a calculator, and you did not want to give up, which we never want to give up, we can say, I wonder if we can learn something from here. Maybe the graph is going to help us. So if we want to graph it, the velocity from time 0 to time 6, what would it look like? Well, this, I'm hoping you might represent, it's a part of a circle. If you have v squared plus t squared equals 9, and you solve for v, you get v equals plus or minus the square root of 9 minus t squared. So this is just the bottom half of a circle of radius 3 with the origin at the 0, but we don't care about anything to the left of 0. So really it's just a quarter of that circle. And if we have to find an integral, we know that integrals are very similar to area. And I can find the area of this. It's just 1/4 of pi r squared. And r is 3. So it's 9 pi over 4. Pi r squared, but we only have a quarter of it. And then, this is just a straight line. So when t is 3, you get 0, and when t is 6, you get 6. So we can find the area of this. It's 1/2 the base times the height. So that's going to be 6 times 3 times 1/2 is 9. So from that, can we find out what the distance is? Yes, it's 9 pi over 4 plus 9 miles. Wow. In 6 seconds, Amy went that many miles. She is one fast ant. Now, what's the displacement going to be? This is below the x-axis, so it's going to be minus 9 pi over 4, and this is plus 9. Now, she started out at this point here, and she's moving along the line y equals 3, and she displaces this much. So what we have to do is say she's going to stay at the same y value, 3, but the x value is going to be what it started out to be, 2, plus the displacement. So it would be 11 minus 9 pi over 4. And that's where it would end up. So anyway, sometimes not knowledge of graphs and knowing that integrals are so tied to area that they're really signed area that we can actually do it without integrals. Anyway, those are 3 pretty good examples of distance displacement, which is a pretty good use of calculus. So hopefully we'll kind of finish this chapter up in our next talk. Have a good day.